Hi again, AP Calc students. Here's lesson 6.3, something called integration by parts. This will probably prove to be the toughest lesson in this chapter 6. We're going to spend 3 days on it, I think. So it is kind of nasty, as we say. And notice, as I say here, we use this for really nasty integrals. Most of the time they're products of unrelated terms. And how to derive this is based on the product rule. We might in class actually show how this formula is derived. Anyway, here's what we'll begin with, and we will split up the function. Again, usually it's a product into two parts. One we'll call u and the other part we'll call dv. So one will be the function, and then we're going to call the other part anyway, the derivative of some function. And here's what we're going to end up with then. uv minus the integral of v du, and then what we want to be able to do eventually is to be able to figure out what this integral is. And if we're lucky, this integral will be fairly nice and we can evaluate it. So here goes. Be patient. I'm going to show you about 3 examples here, and again it's going to take us a while to slog through this the next few days, but here we go. Alright, so here's my first example here. And notice it's x, the integral of x times e to the x dx. It's a product. They're two unrelated terms. Now, this box might be kind of helpful in helping us figure these out. Basically, what I have here in the box, and notice I have these two shaded boxes, this has to be the entire integral. So one of these parts we're going to call u, and the other part we're going to call dv. And I'm just going to do a couple examples here first, then I'm going to share a strategy for how you would tell one from the other. Sometimes it doesn't really matter, but other times it might a little bit. Alright, so first of all, then in this case, I'm going to set my u part equal to x, and my dv then is going to be whatever else is left in that particular integral. So it's got to be e to the x dx. So notice that everything in the white here, this is my entire integral. Alright, now I'm going to use my derivative rules to figure out these other two blanks. Well, if I start out with x, what's the derivative of x? Well, it's just 1, or 1 dx, basically. And now I have to go in reverse direction here now for, I'll just draw an arrow here, we're going there for the derivative. Here I have to go backwards again for the integral. So if my derivative is e to the x dx, what's my original? And that's going to be e to the x. Remember, the derivative of e to the x is the same thing. Might have to use the chain rule at some point. Now, think back to that formula that you just wrote down here a second ago. And that is, I'll just write it down again. Here's what we have. Integral of u times dv. The formula of integration by parts says it's going to be equal to uv minus the integral of v du. Alright, now how do you tell what to put in here? Well, it's uv, so I'm going to switch colors here again. So uv, according to my little chart here, would just be x times e to the x. So far so good. Then I have the integral of v du. So as you can see, that's the kitty corner part of this box here. So I'll just write that in there. That's going to be e to the x dx. Now again, if possible, I want to see if I can evaluate this integral. That's our final answer here. Should not have any integral sign in it. We want to just write it as a particular function. So of course we still have our x, e to the x, and by this time you should be able to figure out what's the integral of e to the x? Well, it's the same thing, just e to the x. So then I've eliminated the integral sign and the dx. And of course on these indefinite integrals, the last thing I have to write is plus c. So there we go. We've done our first integration by parts. And granted, I'm going to do a couple of fairly easy ones here just so you can get the hang of it. We're going to be doing some much more difficult ones in class the next few days. Alright, coming up is example number 2. Alright, so similar type of problem perhaps. But let's just take a look at it and see what we can come up with here. x sine of x dx. Once again, I think I'm going to let my u in this case be x. And my dv, remember that has to encapsulate the rest of the integral. U and dv have to take up this whole space, so to speak. So then I have to say that this is going to be the sine of x dx. Now I just use my integration rules here and my derivative rules to find the rest of it. If u is x, du will just be 1 dx once again. And if my derivative is the sine of x, well, what function gives a derivative of sine? Well, it has to be negative cosine, I believe, right? Derivative of cosine is negative sine, so that has to be negative in order to do that. All right, now I just follow my formula again. Perhaps I'll write it down again just so we can remember it. Remember, here's what I'm doing, u dv like that. So u times v minus the integral of v du. All right, I'm just going to fill in the blanks. My uv, x times negative cosine x, so I'll just write it like this. And minus the integral of v du. Well, notice when I am multiplying v and du together, there is a negative sign there. So if I'm minusing a negative, I'm going to change this to a plus sign right away. And then I'll just put the cosine of x dx like that. All right, really just one more step. Minus x cosine x. And what is the integral of cosine? In other words, what do I take the derivative of to give me cosine? Sure enough, it's just going to be sine. So sine of x. And of course, don't forget to tack on the plus c. Now, I should tell you that when we do more complicated ones of these, it's possible that even when we go through these integration of parts the first time, I'm going to get something here that's still not real nice. And sometimes I might have to go through this whole process again just to break this down. So they do get to be a little bit nastier, that's for sure. Now, how do you decide what u should be and what dv should be? Well, here's a couple things for you to write down. U should be something that simplifies when differentiated. In other words, you can take the derivative of it fairly easily. And then the dv should be something that remains manageable when integrated. So you don't want to pick anything that's going to be too difficult. Now, some people use this little mnemonic device to tell you what u should be equal to. And you just kind of go down the hierarchy here. If you have any logarithm, any natural logarithm, for sure you want u to be equal to that. And then an inverse trig function, we won't do much of those. Here's probably the most common one, a polynomial. That would be any power of x or any expression like that. We will want that to be equal to u most of the time. Then any kind of exponential, and then finally a trig function. It's just kind of a hierarchy how to choose that u value. Alright, one more type of example here we're going to look at. And this is something called tabular integration. And you'll really enjoy using this because it's very structured and it's pretty easy to do. And so I'll kind of take you through one example. Again, we'll be doing quite a bit of this in class, certainly, when we get to that point. So let's take a look at it. So tabular integration says I pick one of these parts. Again, it's a u and a dv essentially. And I'm going to just write down all the derivatives of one and then write down all the integrals of the other. Alright, so I'm going to start out with my x cubed here. So I write that down. And then I just go down and do derivatives of that. So when I'm going down in this way, I'm doing derivatives. So I'll just write, I don't know if I want to use y, I'm just going to say derivatives for going in that direction. What's the derivative of x cubed? Well, we know that that's 3x squared. What's the derivative of 3x squared? 6x. Derivative of 6x, derivative of 6. I just keep going down until I get to 0. Now, what I want to do on the next part is I'm going to write down the cosine of x, but now I'm going to write down the integrals. So, in other words, I'm kind of working backwards here with this. So not what's the derivative of cosine, but what's the integral? Well, it's going to be sine. Because from the bottom up then I could do derivatives. The derivative of sine is cosine and that type of thing. What's the integral of sine? Well, it's negative cosine of x. What's the integral of negative cosine? Negative sine of x. And so on and so forth. This one's going to be cosine, like that. You can check to see if you did this right by just starting from the bottom up and seeing if you have the derivative of each one. So the derivative of cosine is negative sine, derivative of negative sine is this, and so on and so forth. Now here's where the kind of cool part comes in. What I'm going to do next here is draw little arrows, and I always start with this first one and go to the next one sort of a diagonal like that. So I just match them up like this. Your first and last entry won't have anything involved with it, but that's fine. Then I put some signages here. I always start out with a plus sign, and then I just alternate my plus and minus signs. It works like this every single time. And now I just follow the arrows and write down my actual integral, which is pretty cool. So here's what it will be. See if you can follow along here. So I start out with plus. I start out with this one right here, so it's going to be x cubed times the sine of x. Again, that came from just starting here and doing this multiplication following the sign out in front. Okay, next one here. Now notice I have two negative signs here, so that's going to turn that into plus 3x squared cosine x. So far so good. My next one will be minus 6x sine x. And my last one will just be negative 6 cosine x. Don't forget, of course, to tack on your plus c, and voila, we are done. That's called tabular integration. That's pretty slick. I should say that it does not work for every single integral, unfortunately, but it is very nice method to use that we'll certainly employ from time to time. So it's kind of good to look for that. Sometimes I'll probably say on the test, use tabular integration for this, and then maybe there's one problem on the test where I won't say that, but it would certainly make sense to use that. Alright, thanks for watching. It gives you a good intro on this integration by parts. Tough stuff, but we'll be working on this for a few days. Farewell.